Okay, so guys, let me show you what's important, and then we agree on a few things. I want us to agree on a few things that we've touched on already. Oh my days! Come on, don't tell me again. Oh, come on. Why? We just wanna quickly wrap it up, okay? It won't be too long. Right? Let me change to a different. All right. We know that we said when you talk about IGCSE Chem, chapter 7, which is out of 12. Okay. I'm going to run 8, 9, 10, 11, 12. Okay. 11, we've touched on it, but we'll do it, finish in 12. So we say acids and bases. I'm going to do things that are surrounding chapter 11, which is organic chem. The other questions that are on rates of reactions and also on a few reactions that I'm going to finish here on acids and bases, so that you can actually do anything called organic chem. Because I'll explain. Okay, I'll show you why I'm doing it. It's like it comes together with organic chem. What I'm doing. So everybody, look here. This is chapter 7. Just remember that this is chapter 7, and we are doing acids and bases. And I told you that when I say you are good, you understand acids and bases, you must be able to understand, number one, properties of acids and properties of bases, right? Properties of acids, and then the properties of bases. Okay, properties of bases. Do you guys know them, right? Properties of bases. Their reactions, the reactions of these things. What I would love you to do is sometimes go back and rewatch some of the videos we would have done to reinstate these things into you. And I said last time we also talked about strong acid, okay? What did I say we use to separate a strong acid from a weak acid? We said it is the amount of ionization in water. We said a strong acid completely ionizes or separates in water, and a weak acid doesn't. Okay, and we saw now the difference between a concentrated acid versus dilute acid. Do you remember? Students, do you remember? And we said when we talk about concentration, we are talking about how much do we have of the acid in the solution? How much do we have? It has nothing to do with how much it separates. And we saw that if you bring a weak acid and you put a lot of it, it doesn't make the solution more acidic. Okay? It doesn't necessarily make the solution more acidic, because you can bring a lot of a weak acid, but a high concentration of a weak acid, which means there's a lot of it in the solution, but remember, it doesn't separate. It hardly separates, so the solution won't be very acidic. But if you bring a strong acid, it may not even be concentrated, it may be dilute. I mean, it's just a little bit of it. But because all the acid you put in that solution will separate and become H plus ions in water, that means you have a very acidic solution. Remember that. You can go back to that video where I talked about it. Today we are continuing to the last bit in this area, then we go to the next thing. Are we together, guys? I also told you about indicators, right? Guys? Hello? Guys? let's finish on. We talked about indicators. You can go back and watch if you've forgotten. I need you to remember those things. You just need to make sure you know all of them. Now I want to be doing the last part, and I think I or kind of did it. I think I don't remember, but I think I kind of did it. But I'm just going to do it right now. Let's talk about oxides. Okay, let's talk about classification. We are doing the sixth thing. Let's talk about classification of oxides. Classification of oxides. Then we can go to salts after this. Classification. Then you are moving towards finishing this chapter. This chapter, for you to say you know it, you must know the properties of an acid, and in other words, what are the ways that we can define an acid. We say it in chem, we define things using their characteristics. If we are defining an acid, please tell me what it does when it goes in water. Please tell me how it behaves when you put a litmus paper, a blue one or a red one. Please tell us what happens when you put a phenolphthalein indicator. Please tell me what happens when you put a methyl orange indicator. Tell me the color you see when you see an acid. Tell me what it does. Tell me what it does. And also tell me for a base. Tell me that. Also tell me the three characteristic reactions of acids. Tell me what happens when I take an acid and a metal. What do I get? Tell me what happens when I take an acid plus a base. What do I get? Tell me what happens when I take an acid plus a metal carbonate. What happens? Then go to bases now. Tell me what happens when I take a base and I react it with an acid. What are you going to get? You need to know the two important characteristic reactions of bases. For bases, you only have to know two. For acids, you have to know three. Okay? For bases, you also need to know its reaction with an ammonium salt. What happens when you take something with NH4 and then maybe Br or Cl like this, and it meets your base, NaOH? We said, what does it do? It behaves just like an acid. Why? For an acid, there is a part that it never gives away. What is the part? The H. For a base, what is the part? The OH. It never gives its OH away. So who does the base give? The Na. And who does it react with? The Cl. So it becomes NaCl to form your salt. Then what do you now have? One hydrogen will actually be given to OH, and it becomes H2O. Then what happens? This NH4 has given away one hydrogen. It remains as ammonia, NH3. This is what happens. You must know this. Okay? Are we together? And we said you can test any ammonium salt by reacting it with a base and testing for ammonia. Really? Yes. Ammonia has an effect of turning damp red to blue. So this guy called ammonia, it turns damp, which means wet, damp red litmus paper to blue. Are we together, students? So we can test for an ammonium ion, this NH4 plus, by reacting it with a base or with an alkali, and then we test for ammonia. Thank you. Now we move on. We are talking today about, those are the two reactions of bases: base plus acid, then base plus ammonium salt. You're done. Then you can talk about any other thing, but now we are moving on. We don't have time. We move on now. What should I know? How to classify oxides, right? Oxides is oxide is a combination, any combination of oxygen and at least one other element. Oxygen and at least one other element. This gives you an oxide. Are we together? Example of an oxide, we put examples, will be MgO, magnesium oxide, zinc oxide, sulfur dioxide, water is an oxide, carbon dioxide. All these are oxides because oxygen is combining with something. Potassium oxide. Oh, so all these are oxides? Yes. Come on now. These are oxides because you can see oxygen and you can see something else which is not oxygen. The moment you see something like that, that's an oxide. Are we together, students? Students, are we together? Hmm? Are we together? All right. Good. Now, how do we know when the oxide is acidic? How do we know when the oxide is basic? How do we know when the oxide is amphoteric? So after doing all these, the reactions of acids and bases, and knowing about them, and knowing what a strong acid and weak acid is and everything, and dilute versus concentrated, the last thing I have to know is oxides. Yes! Are you sure, sir? Yes, I am. I'm very sure about it. Okay, what should I know? What should I know about oxides? We want to know which ones are acidic, which ones are basic, and which ones are what we call amphoteric. So let's start with acidic oxides. Okay? Acidic oxides. Acidic oxides. Let's go. Okay? These are formed when a non-metal combines with oxygen. So when you have oxygen and a non-metal, you are going to get an acidic oxide. Okay? And as this is why fizzy drinks are dangerous. Common examples. Because what makes a fizzy drink go fizzy like that, we call it the effervescence, is this guy called carbon dioxide. But guess what he is? He is acidic. When it dissolves in the water part of your blood, we'll talk about the composition of blood. Okay? When it dissolves in the water part of your blood, it will make it acidic. So carbon dioxide in you is an acid. So you will begin to have acids in your stomach. And also the sugar in it, the sugar in fizzy drink is also dangerous. And also the carbon dioxide, because it goes in your blood and makes an acidic solution there, which is dangerous. So fizzy drinks, no. So when I get rich, I'm going to buy them. And a lot of them. What are you saying? That's wrong. Come on now. Leave them alone. NO2. Are we together? Students? This guy is an acidic oxide. Tell me why you say that. Why do you say carbon dioxide is an acidic oxide? Why do you say sulfur dioxide causes acid rain? Why do you say when it dissolves in rain, it becomes acidic? Why are you saying that? Where are you getting all that? Because it's a non-metal, carbon or sulfur or nitrogen or silicon. These are non-metals. When a non-metal combines with oxygen, we get an acidic oxide. That's a rule. Do you hear me? Am I being heard, guys? Students? All right. Let's go to the next one. So that's not even a question there. So when they tell us about acid rain, hey, fizzy drinks becoming acidic in the stomach, it is because there is a non-metal combining with oxygen. So we are not even going to be surprised. That's what non-metals do. When they combine with oxygen, we have a problem. Okay? So to prove that you actually get an acid there, okay, they react, these non-metal oxides, they react with bases. Really? Yes. To form salt and water. Really? So they do a neutralization reaction. Yeah, because they are acidic. To form a salt and water. Are we together? When dissolved in water, they form an acid. That's why there is acid rain, yeah. And that's why they dissolve in the water part of blood, yes. And cause it to be acidic, yes. When dissolved in water, when dissolved in water, they produce an acidic solution. Question? Anyone with a question? Now, let's keep going. Basic oxides. Basic oxides, yes. Which ones are those ones now? Okay. When a metal element, when a metal combines with oxygen, a basic oxide is formed. When a metal combines with oxygen, you get a basic oxide. Are we together? Don't let me down. Students, don't let me down, guys. Boys and girls. Let's put examples. You have copper oxide. You have calcium oxide. What are they forming? These are forming acidic. Acidic. What? Metal and oxygen. Are we together? So they dissolve in water? Yes, they are soluble, these oxides. When dissolved in water, they produce a basic solution. How do you know? High pH. Very high pH, yes. When pH is above 7, that's a basic solution. When pH is below 7, that's an acidic solution. When pH is 7, that's a neutral solution. So, when a metal meets oxygen, we'll get a basic oxide. Yes. Oh, come on. All right. What about now the last type, which is the third and final? Amphoteric oxide. Amphoteric oxide. Let's go, guys. Amphoteric oxide now, the last one. Okay? We actually have a type of oxide also called a neutral one. Okay? And I'll give you the neutral oxides. But we start with amphoteric oxides. Are we together? Amphoteric oxides. They can behave both as acidic oxides and basic oxides. Okay? Depending on whether the other reactant they are reacting with, the other reactant is acidic or basic. Okay? Are we together? In both cases, salt and water is formed. Oh, really? Yes. So amphoteric oxide plus base gives you salt and water? Yes. And amphoteric oxide plus acid gives you salt and water? Yes. Oh, so it can behave as an acid when it's meeting a base? Yes. and behave as a base when it's meeting an oxide, an acid? Yes. It can be either one. It is both. It's a 2-in-1. We call it a double whammy. 2 at one go. Right. So, common amphoteric oxides. Which ones are those ones that you must know? Common amphoteric oxides. Oxides that can behave both as acid or base depending on who they are meeting. Zinc oxide. Zinc oxide can be an acid, it can behave as a base. Aluminium oxide. Aluminium oxide. Aluminium oxide and zinc oxide are amphoteric oxides. Are we together? I want you to know that zinc hydroxide and aluminium hydroxide are also amphoteric hydroxides. Their hydroxides are also amphoteric? Yes. What? They can behave as a base? Yes. And as an acid? Yes. Whew. That's a lot. But you have to know these ones, the oxides. They can behave as a base or as an acid. Are we together? Examples of Al2O3 being amphoteric. Being amphoteric would be Al2O3 meets hydrochloric acid. What happens? It's meeting an acid. So because this is an acid, it is going to behave like a base. Oh, really? Yes. And we know that the acid will not give anyone its hydrogen. So who will it give? It will give away the chlorine. The chlorine will take aluminium. So you have aluminium chloride plus the hydrogen meets water, and you have 3 waters. There we go. Question? Here you should put 2 of them. Questions? So here it behaving as a base. Then we take the same guy. We now make him meet a base. He will now be the acid. Why is he? Because the other one is the base. That's obvious. What happens now? The base will never give you its OH. So who will the base give you? It will give you the Na to meet with who? With O3. So you end up having, it will meet with, Na will meet with O3 and also with Al. So let's just do it. So you're going to have now sodium, aluminium, oxygen. And it's going to be like this. And now this OH takes one what? This OH, we just need to add more of them so that we get an H2O like this. And that is enough. Are we together? So that means here we'll need 2 of them. And we have our salt and our water. This is it behaving as an acid. Right. Are we together? Let me give you something. One last thing, which is just one line. put it as the fourth. And I want you to say, you must also know that you may be asked about neutral oxides. Okay. This is the last thing you needed to know about oxides. Neutral oxides. Okay. Neutral oxides. Right here to say, there are some oxides that do not react with either acids or bases. They do not, key thing here, no reaction. They do not react with either acid or base. And, okay, these are neutral oxides. And you can say examples would be nitrogen oxide, nitrogen monoxide, and carbon monoxide. These three are all neutral. Questions? Questions? Right. Here is the last thing now that I will need you to know. I want you to underline like this, and I want you to write preparation of salts. I'm going to give you more info today. I'm going to give you one last thing. We are now in part 2. So underline nicely, and we are now doing part 2, which is where this chapter finishes, which is preparation of salts. Preparation of salts. And what I'm starting with today, part 1, is solubility rules. Then I will explain everything in the next lesson. Remind each other with you what a salt is and why we actually do this. Because you say to me, sir, didn't you say that things like table salt, you find them at the sea? Yes, it's true. Didn't you say you mine it? Yes. So why are we now preparing a salt? Why are we in the lab making a salt? Why are we doing that now? Because some salts you can't get them from nature. So what do you do, sir? You have to make them in the lab. Really? Yes. And how do you make them in the lab? You apply solubility rules. Really? Yes. Can I get a question? Yes. Does it tell me the things I'm mixing? Yes. Then does it ask me some questions? Yes. This is an easy question that comes in the exam. But let's just write solubility rules. And I want you to start with A, the guys that are always soluble. We want to know the salts that are always soluble. Instead of guys, you can say salts, or instead of salts, you can say guys that are always soluble. These ones are called neg-seg. These are the guys that are always soluble. I want you to say this G is group 1. This other G is group 7. This N is nitrates, which is NO3, always soluble. This one, acetates. If you want, you can say ammonium salts. Anything with an NH4 is soluble. Then group 1, anything with a sodium, potassium. Do you understand? Are you seeing this? These are going to be soluble. Then these are the S. So the G's are for groups, group 1 and group 7. If you meet something that has anything from group 1 or from group 7, it will be soluble. A compound that has sodium in it is soluble. A compound that has chlorine in it is soluble. A compound that has NO3 in it is soluble. A compound that has NH4 in it is also soluble. And I want you to know that here this S represents sulfates. Sulfates are always soluble as well. SO4 2 minus. If you see anything which is SO4, then it's soluble. Then here we say acetate. Acetate, yes. Acetate comes from acetic acid, which is vinegar. You always put it in your chips. Huh? You like vinegar. Vinegar is also in chem called ethanoic acid. So when we now have acetates, they are from ethanoic acid, which is like this. But this is ethanoic acid, but now you remove the hydrogen and you get something like this. So this is where you have these acetates. So it's from ethanoic acid or acetic acid. The word acetate or acetic acid is from ethanoic acid. So this is what we have as your acetates. Then we have your group 7, which is your chlorine, something with something, okay? Something with chlorine, something with bromine, something with iodine. These are all like that. Question? No question. Anyone with a question here? Hello? Right. Now, I'm going to give you exceptions before we do B. Exceptions, I want you to write car, straw, bar, which means calcium, strontium, barium. Calcium, strontium, barium. These guys are a problem. So we are first going to write the word neg-seg. Then we'll write castrobar. Put castrobar. I'll tell you who it affects. Leave it like that. Let's go to B before we do this. Let's say guys that are normally insoluble. That are normally insoluble. Okay. By guys, you say salts that are normally insoluble. Which ones are those? The stubborn ones. Here we've seen the good guys. You should write them down many times. When you get a question, you go to the back, you put this quick. The bad guys, who are they? Let's put them now. We want to see the guys that are normally insoluble. Okay? Let's put them. The guys that are normally insoluble. Going to say here. say C. This is carbonates and chromates. Two of them. This only happens with C, okay? It is two things. Carbonates, CO3, chromates, CrO4. If you see a CrO4, or if you see this, then you know you are dealing with something that is what? Insoluble. Are we together? Guys, are we together? Are you seeing insoluble salts? Carbonates, chromates. This is where it starts. These are insoluble. Almost all the time. Please remember that carbonates and chromates are insoluble. Okay? Then you put H. Then you put P. Then you put S. You write the word chops. This will be hydroxides, which is anything that ends with OH. This would be oxides, most oxides. I'll tell you which ones are soluble. Then these ones are phosphates. Okay, phosphates are things that end with PO4. Then this is sulfides. Okay, which is just something that ends with an S. Sulfides. So you write the word chops, you would have put the normally insoluble things. This is a very, very important mnemonic. Just like NEGSEG. NEGSEG, thank you. Chops, thank you. You are the normally insoluble. It's easier. Normally insoluble, it's easier. It's chops. Now, what I want you to know is that rules don't actually fight. So we know that hydroxides are insoluble. We know that carbonates are insoluble. We know that chromates are normally insoluble. But when they meet group 1, they will automatically become soluble because group 1 can never be insoluble. When they meet group, let me write it here to say, when you meet group 1 and ammonium, NH4+, when these guys meet them, then they will be soluble. Okay? Always soluble. So I know that carbonates are normally rocks. I know that. Carbonates are insoluble, and hydroxides, and chromates, and oxides, and phosphates. I know that. But my friend, listen. When they meet group 1, they will dissolve. Even if it's a carbonate, yes. When they meet ammonium, they will dissolve. Even when it's a carbonate, yes. Are we together? But when they meet anything else, they will be rocks. Insoluble. Then these guys that end with ide, oxide, sulfide, hydroxide, these three, when they meet your group 2, they will be soluble. Okay? These guys that end with ide, soluble with group 2. Soluble with group 2. We're going to do it again together. Practice this, then apply this. In the alternative to practical, yes. In the theory paper, yes. So write this. Soluble with group 2. The ide. Right. Then it's done. Here, this affects group 7. Is affected by these guys. Sulfates are affected by these guys. They will be soluble. they will be insoluble rather when they meet these guys. Right. We're going to build more on this. Keep this table the way I've given you. I'm going to ask for these notes. This is a very special thing. Please, everybody, keep this. We take it from this in our next lesson. Are we together? Students, we are almost done with this topic of acids and bases. We've done the first part. You're good. Now we are going to see how do they play with salts in the lab to make salts that you cannot mine. How do they make salts that you cannot mine? If it's table salt, they will just go and get it by the sea. Not these, but there are some salts that they can. So we'll see how they play around with it to produce one which is insoluble, which we'll be calling a precipitate. They want to produce a salt which we can collect at the bottom of the solution, which we call a precipitate, and use, or one which will stay in the solution when the other one is going out, and then they will evaporate the water and take the one which would have remained in solution. We'll see how they do that. Don't worry about it. As of now, I'm happy with the progress. I'm happy with what you've done, and I'm dismissing you guys. Good night. If you haven't seen the questions, I'll repost the maths assignments. I got some questions from some people who wanted to see it, and because I need it before tomorrow's lesson. And that's it. And the notes for today. Submit in the links that I'll put soon after this lesson. Submit the notes and the assignment. As of now, goodbye, everybody. We meet tomorrow.